Good evening, sir. Number 85 43 60 26.
Good evening, sir. Dr. Sunil Kumar, sir. Dr. Sunil Kumar, sir, am I audible? Sir, you are unmuted and you can talk.
Yes, sir. Audible, sir.
Dr. Sunil Kumar, sir. Sir, good evening, sir. Dr. Sunil Kumar, sir, please unmute your mic. Yes, sir. Please share your screen, sir. Sir, your voice is not audible.
Sir, now audible,
Sir?
sir? Sir, my voice
Yes, sir.
audible?
Fine. Fine, sir.
Okay, okay. Thank you very much,
Sir, shall
sir.
we start?
Sir, now, can I start, sir?
Sir, please wait. Let me start first, then we can.
Okay.
So, good evening, everyone. I welcome you all to the fourth day of six-day faculty development program on recent advancements in materials, manufacturing, and technology, organized by Department of Mechanical Engineering, Swarnandhra College of Engineering and Technology, West Godaveri District, Narsapur, Andhra Pradesh. This will be a six-day program with a live stream session on the same timing from 6 to 8 p.m. We do expect you to attend all the 6 days, and this is the fourth day of our FDP. 2 more days to go. And if you have any trouble in attending online session, you can join using the YouTube live stream, using the link which is posted in the WhatsApp chat box. So we would like to welcome today's session one resource speaker. Now, moving on to the today's session, let me first introduce today's resource speaker, Dr. Sunil Ratna, Professor from Sir C.R. Reddy College of Engineering, Eluru, West Godavari District, Andhra Pradesh. Sir has completed his master's in machine design during the year 2002 and completed his PhD in mechanical engineering from Andhra University, Visakhapatnam during 2019. Sir has the professional experience of 20 plus years working in various institutions and having a research publications of around 15 journals in national and international, and three conferences and one patents granted. And SAR also has guiding uh, 8 PG and a more number of undergraduate students. So he has attended several webinars, workshops, and conducted certification completed programs, and also professional body membership in IEI, and he is the coordinator for NBA, NAC, as well as for coordinator for BTech UG programs. Also acted as IEI faculty coordinator for various departmental activities and acting as a member in Board of Studies in Usha Rama College of Engineering since 2021. So with this short introduction, I welcome you, sir, and go over to you, please.
Thank you. Thank you very much, sir. Sir, first of all, respected management, principal, HOD of Mechanical Department, and other staff, all of you, very good evening, sir. This is Dr.K. Sunil, Dr. Kumar, Associate Professor, Department of Mechanical Engineering, sir, REDDY College of Engineering, Eluru, sir. Today I am here to give a lecture on composite materials by using powder metallurgy technique. So, coming to the contents in my lecture, first of all, introduction, then types of composites, then fabrication methods, powder metallurgy method, advantages and limitations of powder metallurgy method, applications of powder metallurgy method. Then one more example is there. So this example belongs to the method of fabrication powder metal by using powder metallurgy. One problem is there. So one fabricated problem. One problem is that this is related to powder metallurgy technique. Then coming to the introduction. So first of all, a definition of composite. You know about definition of composite. Composite consisting of a combination of two or more materials. These materials are does not dissolve in each other. So composite material used in various sectors due to enhancement of their properties with respect to base material. So composite material consisting of two or more materials because of different properties of these two materials. The final component is having enhanced properties. Then coming to the properties. So here, depending upon the type of matrix. So you are going to, we are concentrating on metal matrix composite. So in this metal matrix composite, so first of all, the properties are depending upon matrix, a type of matrix. So there are different types of matrix and different types of reinforcements are there. So these properties are depending upon the type of matrix we have chosen, then type of reinforcement and the size of the particles and the size of the reinforced particles as well as method of fabrication. Then the addition of reinforcement leads to increase or decrease of some of the properties like hardness, toughness, tensile strength, and other mechanical properties. Then coming to methods of fabrications. So different methods are used to fabricate composites. So in this infiltration method is there, a different dispersion method is there, spraying, in situ fabrications, field casting, compo casting, diffusion bonding, and powder metallurgy. So among all these methods, so I have been selected powder metallurgy method. Why? Because so this method is having some advantages. So this is a simple method for the mass production, better surface finish, less wastage of material, uniform distribution of reinforcements in alloy and linear shapes will be obtained. Then coming to types of composites. So composite materials are two types. One is matrix type, second one is a reinforcement type. So different types of matrix can be used for the fabrication of composite. So in this matrix type of polymetric matrix type is there, ceramic matrix is there, metal matrix is there. So in polymetric there are two types. So one is the thermoplastic and the second one is thermosetting plastic. Then coming to ceramics, so various ceramics materials can be used for the fabrication composites as a matrix material. These are some examples are glass, alumina, silica, etc., etc. Then coming to metal matrix, so different metals can be used as a matrix. So some of the examples are aluminium, copper, tin, nickel, etc., etc. Coming to reinforcement type, so three types of reinforcements can be used for the fabrication of composites. So one is a whisker, so this is just like a fiber, but the very thin layer, just like hair, can be used for the fabrication of the composites. Then coming to fiber reinforcement composites. So fibers are of two types. One is continuous type of fiber. So second one is a short fiber. Coming to continuous fiber, so based on the arrangement of the fibers, so unidirectional and bidirectional. Then coming to short fiber, other one is short fiber. So these are randomly placed, or sometimes in same line. These are aligned. So fiber composites are there. After that, so particulate. That means the particles can be used as a reinforcement. So these are coming under particulate type reinforcement of composite materials. Then coming to different methods. So first of all, infiltration method, then dispersion method, spraying, in situ fabrication, squeeze casting, steel casting, compo casting, diffusion bonding, powder metallurgy. All these are used for the fabrication of metal matrix composites. Among all these, powder metallurgy is selected for the fabrication of composites. Then coming to a methods. Powder metallurgy method. So coming to powder metallurgy method, first of all, powders are considered. Different metallic powders are considered. So it is the science of producing fine powders and then making objects from individual mixed or alloyed metal powders with or without the inclusion of non-metallic powders. So different powders, metallic powders are considered for the fabrication of composite for the powder metallurgy method. Then this method involves producing metallic powders. So different methods are there for the production of metallic powders. Then blending them, or this is also known as the mixing of powders. Then after that, pressing or compacting the mixed powders into required shapes. And finally, sintered the pressed green compact. So the compacted component is known as green compact. This green compact after compaction will be sintered to improve the properties. Then final product in this method, the components are produced in their final shape by pressing the metal powders into the desired shape, then heating the compacted powder for a period of time. So for different materials, we are going to use the different temperatures. Then coming to secondary operations. So after sintering process, so sometimes the secondary operations are required to enhance the properties of the final product. Next, coming to powder metallurgy process. So this is the process. These are the used for the fabrication of powder metallurgy component. So first one is powder production. So this method involves first of all powder production or production of powders, production of metallic powders. Then these powders are blended or mixed by using different machines. Then after this blending, blended powder is a compacted powder will be sintered to enhance the properties. Then at last finishing operations. So some more properties will be improved in finishing operations. So this is also known as secondary operations. Then coming to powder metallurgy process. First of all, so we have to select different metallic powders. Then these powders will be added to some additives. So these additives are stearic acid or sometimes graphite can be used as additives. Why? Because during a compacting process, so friction will be induced. To minimize the friction at the time of compaction, so we are going to use additives. Then, so these are blended. After that, so the blended powder will be compacted. Then, so compacted component will be sintered. Then, after sintering, secondary operation may be taken place. So finally, we'll get the finished product. Then coming to powder metallurgy process. So first of all, we have to concentrate on powder. So production of powder. So first of all, we have to produce powders by using different methods. Then this powder will be characterized. Why? Because size of the particles or shape of the particles may influence the final properties. Hence, the powder will be characterized to know size and shape. Then with these powders, we are going to use a powder metallurgy method. In this process, so blending is taking place. After that, compacting the blended powder, then centering is taking place. Then these are forging and hot pressing. So these are the secondary operations. So after that, so final product will be obtained. So we are going to find the properties of the final product. So here are different so density or porosity, ductility, strength, and other properties can be found by using different experiments. Then coming to methods of metallic powder preparation. So we are going to produce a different metallic powders. So nowadays there is no need to produce are already available in our market. So online we can order these powders directly. We'll get the powders. There is no need of producing metallic powders. But to know the methods of producing powders, so these are the methods to produce metallic powders. So first of all, mechanical polarization. So in this by machining, that means simple filing also will use different metallic powders. So then crushing, milling, grinding, etc. So by using this, we can produce metallic powders. Then atomization. Atomization is also a process. So molten metal, if it is cold, then it will be converted different particles. Then electrolysis, then chemical reactions, shooting. So these are the methods to produce metallic powders. So nowadays these methods are not required. Then coming to blending or mixing metallic powders. The process of blending and mixing the metallic powders in a required proportion. So we are going to consider some proportions. Based on these proportions, the final product will give us properties to obtain the desired properties in the final product. Then lubricants such as graphite powder, stearic acid also can be added before blending to reduce die wall friction during compression process. So during compression process, to minimize the friction, wall friction, die wall friction, so we are going to use graphite powder, we are going to use stearic acid. Then coming to blending or mixing of metallic powders, so by using any of these or different methods are there. Among them, these are some of the methods only to mix or blend the metallic powders. In this, ball milling can be used for blending, or a motor with a pestle can be used. Then ordinary lathe can be used for blending and mixing. So in this ball milling machine, so inside this a chamber, cylindrical chamber is there. So inside this machine, a cylindrical chamber is there. So this may be tungsten carbide chamber, or sometimes a chromium chamber is there. So inside that we are going to pour the blended the powder. So what we are taken proportionately. So we have to pour this powder in the crucible in the cylindrical chamber. Then so this cylindrical chamber is so fixed inside this ball milling machine. Then once if it is operated, then balls also included inside the chamber. So steel, but sometimes so chromium balls or sometimes tungsten carbide balls can be used inside the chamber. So inside the chamber, balls are there. Some balls are there, chromium balls. So based on the chamber, we are going to consider balls, different types of balls. So these are mixed. Once if it is operated, then so because of this movement, balls will collide. So because of the collision in between the material, the part will be blended. So this will be operated only for the few minutes, only 10 to 15 minutes. Only that is sufficient. Then coming to mortar with this pestle, the powder, the proportional powder is filled poured in this mortar. Then by using this pestle, we are going to apply some pressure on this powder in only one direction. Then this will be mixed. So lathe also can be used. So it is in this also we are going to consider a hardened steel cylindrical chamber. So inside this we are going to pour material, pour the powder along with the balls. Then if the chamber is rotated by using this lathe, thereby inside the chamber the powder will be mixed. Then so after blending or mixing, so compaction of metallic powder will be taken place. So here die pressing. So this is one process to blend to compact the metallic powders. So the blended loose powder is filled in the die, and then this powder is compressed to the predetermined pressure. So this pressure varies according to the type of material, type of metallic powders. So this may be varying from 80 MPa to 1400 MPa in the die itself to form the required shape. So after compression, the obtained product is known as green product. Why? Because the particles are not perfectly bonded together. So after compression, so the product is just like a chalk piece. So there is no bonding between the particles. Hence, so there is no strength of that component. So to improve that, we are going for the next operation. So for the compression process, so first of all, we require blended powders. Then, so this is the die set. So this is the die set. So this is the hardened steel die. So along with, you are going to consider a punch. So this is the punch. So this powder will be poured inside this hole. Then by using this compacting machine, we are going to apply pressure or force on this mixed powder. So thereby, so this powder is compacted inside this die. Then the compacted powder will be ejected from the die itself. Thereby, we are getting one green compact. So this is the compaction of metallic powders. So same. So this is the die. So this is upper punch. So this is lower punch. So this is the powder. Powder is in the filled inside this hole. Then, so by using upper punch, we are going to apply force. Then this will be compacted. Then this will be ejected by using the lower die, a lower punch. Sorry. So after a compaction, then so next process is a sintering process. So sintering process, there are two categories. One is pre-sintering, and second one is a final sintering. So final sintering will go to final product. So pre-sintering means, so before going to final sintering, we are going to pre-sinter the component. So this process can be continued only whenever machining of the component is required. If there is no need of machining of the component, there is no need of pre-sintering. So if we are going for the machining operation, then only we are going for the pre-sintering process. So here, what is pre-sintering? It is an intermediate process generally undertaken before sintering operation to facilitate some unavoidable machining activities. Before actual sintering process, pre-sintering is carried out whenever the part requires a machining operation. When we are going for the machining operation, then pre-sintering is compulsory. Otherwise, there is no need of pre-sintering. Then it removes the lubricants and binders which added to the product during blending operation. The compacted parts are heated for a short time at a temperature considered below the final sintering operation, final sintering temperature. So final sintering temperature differs from pre-sintering temperature. So pre-sintering temperature is always below the final sintering temperature. Then coming to sintering, final sintering. So sintering consisting of heating the pressed component or compacted component. So this is also known as the green component to a temperature below the melting point temperature of the major constituent. Once if you are using 2 or 3 metallic powders, so sintering temperature is based on major constant of these 3. Then it requires inert atmosphere to avoid oxidation during the process. In this process, the properties of the final component is depending upon sintering time, sintering temperature, heating rate, and also cooling rate. So most of the metals are sintered at 70% or 80% of the melting temperature, the major constituent. Then coming to sintering temperature and timetable. So here different metallic powders are there. So these are the sintering temperatures chosen according to the type of metallic powders. Then this is the time of sintering time. So coming to first aluminum alloys, then sintering temperature varies from 370 degrees to 570 degrees centigrade. Then time for sintering is 24 hours. Then for copper, brass, and bronze, so sintering temperature varies from 700 to 900 degrees centigrade. So sintering time is only 30 minutes. For iron, sintering temperature is 1025 degrees to 1200 degrees centigrade, and sintering time is only 30 minutes. Then for tungsten carbide powder, sintering temperature is 1480, and time is varying from 20 to 40 minutes. So this is the sintering furnace or muffle furnace used for the sintering process. Then coming to finishing operations, so secondary operations. So after sintering, the final product is obtained. So because of use of some binders or additives, so these components are porous. So to enhance the properties of the final component, we are going for finishing operations or secondary operations. So most of these cases, sintered components are directly used for various applications. Whenever super surface finish or tolerance or metal structure desired, the sintered parts are subjected to secondary operations. So these are the secondary operations. So sizing, coiling, infiltration, impregnation, machining, heat treatment, plating, etc., etc. So these are the advantages of powder metallurgy. So here, metals and alloys can be mixed in any proportion. So you can mix reinforcement in any proportion to give desired properties. So metals and non-metals can also be mixed in any proportion. Parts have good surface finish, that the machining is eliminated. Porous parts can be produced that could not be made in any other way. No metal is wasted as a scrap because the process utilizes 100% of raw material. Super hard cutting tool bits, diamond impregnation tools, tungsten carbides are made possibly by this method. So labor cost is low, so high production rate, and so on. Coming to limitations, due to strength, toughness, yield strength, etc. are reduced. Size of the product is limited. Equipment cost is high, hence high initial cost. Production of metal powder is expensive and difficult to store without deterioration. So nowadays there is no need to produce metallic powders. So pressure up to 100 times are required even for small products. Even at high pressure, metal powder do not flow easily and variation in density of component. It is difficult to produce the parts having sharp corners, long thin sections, and also a varying cross section of components. So these are the applications. So porous permeable parts like self-lubricating bearings, filters, porous plugs, pressure and flow regulators can be manufactured or fabricated by this method. So composite parts with refractory metals like tungsten, molybdenum, and melting or casting. Tungsten filament is very small and super hard part which cannot be it cannot be measured conventionally. So complex and intricate parts like small gears, cams, levers, sprockets, etc. can be fabricated by using this powder metallurgy method. Then friction materials like clutch plates, brakes, linings, etc. can be fabricated by using this method. Then coming to powder metallurgy process, so I am going to consider one problem. So this is already fabricated by our students. So here one example problem related to powder metallurgy. So this is a fabrication method. So fabrication of aluminum 2024 B4C. So this is MMC and aluminum 2024 graphite. Here graphite also used. Hence this is coming under hybrid metal matrix component by powder metallurgy method. So this is one example problem fabricated recently. Then coming to experimentation. So in these three stages are there. Stage one is fabrication. Second one is the characterization of the fabricated composites. Then in the third stage, so we are going to find the mechanical properties. Then coming to fabrication of composites. So here three types of materials are used. So one is the alloy, and two more metal powders are reinforcements. So here powder metallurgy method is selected for the fabrication of both metal matrix composites and also hybrid metal matrix composites. So here aluminum 2024 of an average size 50 microns was selected as the matrix due to its high strength to weight ratio, and it is received from Mumbai. Two types of reinforcements, both with an average size, grain size 100 microns, were used for the fabrication of composites. So one is a B4C powder. So this is also received from Mumbai. So graphite powder, this is from Amazon India, online Amazon India. Then coming to received powders. So these are the received powders. So one is aluminum alloy powder. So aluminum 2024 alloy powder. So second one is the B4C powder. So this is graphite powder. So this is graphite powder. So first of all, so FSM analysis was conducted on these received powders. So from this, so these are the some images of the received powders. So aluminum 2024. So these are the particles of aluminum particles. Then so this is B4C. Then so this is a graphite powder. So FSM images of received powders. Then so elemental composition of aluminum 2024. So here aluminum is maximum 90.7 to 94.73. Then so the second one is the copper and so on. Then these are the mechanical properties of so aluminum 2024. Then coming to particle size and density of powders. So these are the materials of these are the materials. So aluminum 2024, B4C and graphite. So average sizes are so aluminum 2024 50 microns, B4C 100 microns, graphite 100 microns. So these are the density. So here so aluminum 2.71, whereas B4C so less than 2.7, less than aluminum powder. Then graphite, this is also much more less than aluminum or B4C powders. Then coming to blending of powder. So after receiving the powder, these powders are weighed proportionately, and these are blended together. So the required quantity of powders for metal matrix composites. So here metal matrix composites are so pure aluminum 2024, then aluminum 3% graphite, then aluminum 3% B4C, then aluminum 6% B4C, and aluminum 9% B4C, aluminum 12% so aluminum 12% B4C, aluminum 50% B4C. So these are only metal matrix composites. Whereas in the second case, so another type of composites are fabricated. So here graphite is used. Hence these are coming under hybrid metal matrix composites. So first of all, the proportionates are taken from by using simple balance. By weighing the powders, we are going to use some proportionate powders. So these powders are first of all mixed in or blended in a ball milling machine. Okay. So for this ball milling machine, the parameters. So these are the parameters which influence the powders. So first of all, milling time. So 15 minutes is considered. Next, milling speed 400 RPM. So milling environment. So inert to cool. Ball to powder ratio 10:1. So ball weight is 10, powder weight is only 1. So by using ball milling machine, these powders are blended together. So this is the ball milling machine. Then so the FSM and EDS analysis is carried out to know elemental elements in each and every metallic powders, as well as so FSM analysis to know structure of each and every powder, as well as each and every component. Then FSM and EDS analysis of blended powders. So this is aluminum 2024. So these are the FSM pictures. So this is pure aluminum 2024. Only aluminum 2024 is there. So these are the remaining. So unwanted components are there. Then coming to second one. So aluminum 3% graphite. So aluminum is there. Then 3% graphite is there. So these are present presented in the microstructure. Then aluminum 3%, aluminum 3% graphite, 6% B4C. So this is the FESM picture. Then aluminum 3% graphite, sulfur B4C. So this is the picture. So these are the FESM analysis of blended powders. So this is for aluminum 6% B4C and so on. So this is FESM. So this is FESM machine used for structural analysis. Next. So after blended, then we are going to compact or press the powder by using a die set. So here the blended powder is compressed at a pressure of 400 MPa by using a compression testing machine. So hardened steel die with a hole of 15 mm diameter at the center and a punch assembly is used for completion of the blended powders. After the compression process, same pressure is maintained for about 10 seconds, then the pellets are ejected out from the die. After the compression process is over, green pellets of 15 mm diameter and 25 mm length are obtained from the die at room temperature. For each run, before commencing for the compression process, approximately same quantity of well-mixed powder is filled into the die. For easy removal of pellets after the compression process, silicon spray. One spray is there. So this is sprayed into the die before going to fill the powder. So gradual pressure is obtained on the powder. So this is the die set. So this is the die. So this is the punch. Then so this is a compacting machine, compression testing machine. So after compression, then green pellets are obtained. Then these green pellets are centered. So this centering process includes a heating of the component. So because of this heating, the grain structure or bonding in between metals may be taken place. So the centering process involves heating the samples in a controlled and inert atmosphere, argon gas, to prevent oxides during the process. The pellets or grain pellets are heated up to the bonding temperature and then they are cooled in the furnace itself. The sintering process followed the sintering cycle at the rate of increase of temperature 10 degrees per minute and heated up to temperature 520 degrees for about 24 hours, after which the samples are allowed to cool in the furnace itself to reach room temperature. The grain growth and grain bonding in between the neighbor particles can be achieved by this sintering process. So grain bonding may be taken place in between the different metals by a sintering process only. Then so this is the sintering furnace, muffle furnace used for sintering process. Then so these are the after final products after a sintering process. So 15 mm diameter and 25 mm length. So these are the final components or final products obtained after sintering process. Then so after the final products, then these components are characterized. So characterization of composites. So by using optical microscope, before going to optical microscope, so we are going to prepare the specimens. So by using hand polishing and also then going for image analyzation. So first of all, before going to examine the specimens on the optical microscope and FESM analysis, the sintered specimens are polished by using a disc polishing machine to obtain mirror-like finish. All the specimens are polished on a standard hand polishing machine shown in figure by using 240, 600, 800 and 1000 degrees silicon carbide papers. Diamond paste is used to obtain mirror-like surface finish during polishing. to expose the structural features. The polished specimens are etched with Keller's exchange solution. The etch and polish etch procedure are used to attain good microstructure. Then, so this is the hand polishing machine. Then, so this is optical microscope to obtain microscopic pictures. Then, this is pure aluminum 2024. So this is microscopy examination. Then this is for aluminum 2024 and 3% graphite. So this is a microscopic examination. This is the picture from microscope. Then this is related to aluminum 3% B4C. So these are the particles, B4C particles. So clearly observe these particles. So these are B4C particles. Then we are going to increase 6% B4C. So these are the particles in an alloy. So this is aluminum 9% B4C. So these are the B4C particles. Then coming to FE analysis. So this will use microstructure. So this is for pure aluminum 2024. This image is aluminum 3% graphite. So there is a bonding in between these molecules. Then this is aluminum 3% B4C. Then this is related to aluminum 6% B4C. So this is FESM analysis. So this is aluminum 3% graphite to 3% B4C here. So graphite particles are there. So B4C particles are there. So aluminum 9% B4C. So this is hybrid composite aluminum 3% graphite to 6%. So the graphite particles clearly observed in this picture. So this is 3% graphite to 9% B4C. So this is a FESM analysis. Then, so after microscopic or FESM analysis, we are going to find different properties. So first, we are going to find the density of the produced composites. So here, density can be found calculated by using Archimedes principle. So this is the equation to find density of the components. So density of metal matrix composite equal to, so M is for mass of the component in Eluru. M1 stands for same mass in water, distilled water. Then this is the density of distilled water H2O. So these are the density value for different fabricated composites. So aluminum 2024. So three tests are conducted. So in this average value is 2.7 for aluminum 3% graphite. So this is the obtained value for aluminum 3% B4C. So this is the obtained value. Aluminum 6% B4C. So this is the obtained value, and so on. So first of all, this is a pure aluminum. Then this is aluminum 3% graphite. Then this is metal matrix composite. So these are related to hybrid metal matrix composite. Why it is metal? Why it is called as a hybrid metal matrix composite? So here we are going to use 3% graphite as well as 3% B4C. Hence these are coming under hybrid metal matrix composites. Then, so this is the density variation of various composites. So this is pure aluminum. Once graphite is added, then the density suddenly decreases. Why? Because graphite is having less denser material. Then, so once if you are adding B4C, so here if you are adding B4C, so there is an increase in the density. Then if you are goes on increasing the B4C content, then automatically the density of the composites decreases. So this is related to only metal matrix composite. So these values are related to hybrid metal matrix composite. So here we are going to use graphite also. Hence, some increase is there, then thereby decrease is there. Then coming to density variation. So this is aluminum. Blue color indicates 0% graphite. That means there is no graphite in this blue color. There is no graphite. There is no graphite powder. there is no graphite powder. So in red color, in red blocks, so 3% graphite is there. So here 3%, this is fixed. So 3% graphite is there. So 3% graphite is there. So here, so aluminum, so 0% B4C means, so this blue color indicates 0% graphite. So that means aluminum, so 0% graphite to 0% B4C. This is pure aluminum. Then, so this red color, so this block indicates, so aluminum 0% graphite, but there is 3% graphite is there. So similarly, this blue color indicates there is no graphite particles, whereas in a red picture, red colors, so there is a 3% graphite particles are there. Then coming to micro hardness test. So this is the micro hardness test. So for aluminum 2024, D1, two directions are taken, at two values are taken for each and every specimen. Then, so percentage of increase of hardness. So this will indicate percentage of increase of hardness values. So first of all, in trial 1, so Vickers hardness, micro Vickers hardness test, number is 135 for aluminum 2024. So in the second case, 142. Then this is the total micro hardness value. Similarly, aluminum 3% graphite. So trial 1, 111.09, trial 2, 137.5. So this is the total micro Vickers hardness number. Then, so this is the increased value. So then aluminum 3% B4C. So these are the values obtained. For aluminum 6% B4C, these values are obtained, and so on. Then coming to hardness values, so these are shown in a bar graph. So here also same as blue indicates 0% graphite. So red color indicates, so there is a presence of graphite, that value is 3%. Then, so these are the hardness values, 138.95, then 144 hardness increases, then 148, then 154. So these hardness value increases. Then coming to conclusion of my work, so aluminum graphite B4C hybrid metal matrix composites are successfully fabricated by using powder metallurgy technique. The microscopic examination shows the presence of reinforced particles in aluminum alloy, and the uniform distribution of particles throughout the alloy. The density of the hybrid composite is less for the hybrid composite due to the use of less dense reinforcement B4C and graphite as compared with the aluminum 2024. The density of these fabricated composites decreases with the increase in percentage of B4C. The micro Vickers hardness of both fabricated metal matrix composite as well as hybrid metal matrix composites improved compared with the base alloy, but there is a drop in micro hardness for hybrid composite due to the presence of graphite. So coming to future work, future scope, the powder metallurgy produced composites are having less tensile, corrosive properties when compared with the other methods. Hence, secondary operations like extrusion, coiling, sizing, cold forging, and hard forging, etc., may result in increase of all the properties. The particle size also influences the properties of the composites. In this work, the used reinforcements are micron size. Hence, there is a possibility to use nanoparticles to improve all the properties. So, thank you one and all. Hello. 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 Hello.
Thank you, sir. Now, participants, you can unmute yourself and you can ask queries.
Hello.
Hello.
Sir, good evening.
Sir, audible, sir.
Audible,
Okay, sir.
Audible, sir. Audible, sir. Audible, sir.
Sir, regarding of
Audible, sir. Audible.
okay, sir, I am Dr. Ismail, sir.
Okay, sir. Nice meeting you, sir.
So regarding of selection of B4C percentage of variation in percentage of B4C and percentage of variation in with graphite. So on which basis you have been selected this composition?
Sir, B4C, sir, sir, graphite is considered only because of once if you use graphite powder, then the products are self-lubricated, sir. Hello.
Sir, I am
So
listening, but
after,
only the thing, my doubt is the selection of the proportion, nothing but 3% of B4C,
to
6% of
obtain self-lubricated component, lubricated property, sir. Sir, this is only one trial, sir. We can increase the reinforcement, sir. Hello.
sir, I am listening to you.
Sir, this is only one trial, sir.
Okay, sir. Apart of that, in your conclusion, you said that the uniform distribution of B4C particles has been noticed from the microstructural image. But
Yes,
when
sir,
it comes to the optical microscopic examination as well as scanning electronic microscopic examination, what I have been observed, no, there is no proper distribution has taken place because let me know the reasons of lack of uniform distribution of the particle throughout the matrix material.
Sir, both the exams we are concentrating at very minute portion, sir. Very minute portion of the composite, sir. Sir, in actual, so these are closer together, sir. But because of we are considering very minute portion of the specimen, so therefore we are getting we are observing there is a lot of gap in between them.
So as per your results, whenever you are adding the graphite percentage, micro hardness is increasing for all hybrid composites as compared with the before composite. So how we can overcome this improvement of the oxygen? Actually, graphite also act as a secondary lubricant, secondary reinforcement.
Yes, sir.
Yes, along with the
Yes,
B4C, B4C also primary reinforcement as well as graphite also secondary reinforcement. So there is much variation in density also have been noticed. So these results, yes, sir. Go for the next step. So just you can see this, sir. Percent of composites like 0%. When you are adding the B4C 0%, you can observe that when a drastic change in what y-axis on the y-axis density has been noticed.
Sir.
So when just you can add little bit quantity of the graphite, a huge variation in density has been noticed.
This is density, sir. So coming to this is hardness picture, sir.
Micro hardness also. You can adjust. You can see.
Scale because of scaling only we are getting maximum value. So 2.7. So this is only 2.7. This is only 2.63, sir. So all
Yes,
these
sir.
are nearer values, sir.
But whenever we are adding the secondary reinforcement, the density also we are going to calculate density. So graphite density also considered, B4 density also to be considered. When it will come to the maximum percent of 15% of B4C composite, the density will be a little bit higher as compared with the pure.
Sir, we are fixing only we are fixing a graphite powder as only 3%, sir.
Yes, sir.
Just we are going to vary B4C powder, sir, 3% to 6% to 9%, whereas graphite is always constant only 3%, sir.
Okay, sir. When we will come to the optical microscopic value, what is the magnification you have been selected for that taking of images?
Sir,
Optical microscopic value.
I don't know, sir. Why? Because our students know about this, sir.
Okay, sir. Thank you. Thank you, sir.
Sir, any queries, sir?
So thank you, sir. No queries. Thank you so much, sir.
So finally, I thank the management of Swarnandhra College of Engineering and also principal and also organizing team, HOD and other faculty members. So I feel this is a great opportunity to interact with you. So thank you very much. Thank you very much, all of you.
So I would like to thank on behalf of Department of Mechanical Engineering for your nice presentation and insightful thoughts about composite materials using powder metallurgy techniques. So thank you so much, sir, for spending your valuable time as a guest speaker for the session 1 and accepting our invitation in a short notice. Thank you so much, sir. Thank you.
Thank you very much, sir.
Sir, thank you. Thank you for your valuable insights.
Thank you very much, sir.
So, dear participants, our second session by Dr.K.Kamalakkannan, professor from SRM University, will be started in another 2 minutes.
Good evening, friends. It's audible. Dr. Francis is audible?
Yes, sir. Yes, sir. Good evening, sir. Audible, sir. Sir, shall we start, sir?
Yes, ma. I'm ready, ma. Plus, I will check it. The slides are running. Only one thing you can confirm with me. One minute, ma.
Sir, make it full screen, sir.
1 minute, ma. One minute, Francis. It's not opening.
Sure, sir. Sir, you can log out and share again.
Log out, I can log in, right? I don't know what's happening. It's not sharing also. Just I'm leaving meeting and join
sharing and try again, sir.
Yes, sir. Yes, sir. Now it's coming. That's it. It's visible.
Yeah, fine, sir. Fine. Let's start, sir.
No, slides are moving.
Yes, sir. Yes, sir. It's moving.
Slides moving. Okay, okay. Then you can start.
So, good evening again. Now moving on to the today's second session by Dr. Kamalakkannan, Professor, SRM University. Let me introduce our today's resource speaker.
Dr. Francis, we are having 1 hour time. I think it's not required introduction all the things, right?
Sir, 2 minutes, sir. Just brief introduction.
Okay.
So, Dr. Kamalakkannan, Professor from Department of Automobile Engineering, College of Engineering Technology, Kattankulathur, Chennai, main campus, SRM, having an experience of 27 years and with research interest in the area of vehicle dynamics, noise, vibration, harness, suspension system, vehicle design and development, electric and hybrid vehicles, has published more number of scientific and research papers in national and international journals, and also received awards and achievements, appreciation awards, best faculty advisor, special awards, and notable achievements like from Germany, supported for Euro 2000 for attending a lecture program. Similarly, John Deere sponsored by 2 lakh to attend a lecture program, and also having a German patent on 3-dimensional printer. Um, Instrumental person for creating UG syllabi in automobile engineering, especially in motorsports engineering. He is also faculty advisor for Bajaj International Bajaj FSAE in his institution. His ability to move the students Dronacharya and Best Faculty Advisor Award during 2011 by SAE India. Having a vast experience, he is instrumental in obtaining prestigious AICT RPS titled Design and Development of Three-Wheeler for Physically Challenged, worth 6 lakhs, and acted as a principal investigator. And his research work involves semi-active suspension system for all terrain vehicles, and he has published more journals and international conferences, currently guiding 2 full-time research scholars. He is also a member in SAE. So with this short brief introduction, let me give our discussion to our today's speaker. Sir, please.
Thank you, Francis. Thanks for introduction. Thank you, friends. My topic is a control strategy of Magneto-Rheological dampers in automotive applications. Right. It's having agenda is abstract, introduction, implementation, various control strategies, challenges, a few case studies, a research opportunity, conclusion. Like the previous presenter, it's not purely talking about material characteristics. This particular title talks about how the material characteristics can be changed by using various input. Right, that is the focus on my topic. Right. So, especially I am belongs to automobile engineering. My PhD topic is a semi-active suspension system, where it's having a compromise between a full active and passive suspension system. And you already know for vehicle performance and handling system, there are 3 components are very, very important: steering, braking, and suspension system. And for suspension responsibility, this I don't want to keep on the presentation. Just I'm running it. Just I'm going for this is a very, very important one. This particular slide is very important one. We always look for 2 things. One is a ride comfort, and another one is 1 minute. Right. One is a ride comfort, another one is the vehicle stability. The problem is if I am having low damping, or I am having a this soft suspension, soft spring, I am having a good ride comfort, not have any problem. But I am having a hard spring, I am having good vehicle stability. So that means I am having a trade-off between my ride comfort and the vehicle stability. I cannot achieve using same spring and same damping by getting ride comfort or vehicle stability. I have to do some compromise on this area, this particular area. I have to do some compromise. So what compromise I do? How I can get it? That is a bigger task to automotive engineers. Not moving. Sorry, it's not moving. 1 minute. It's visible. Right. So I have to look for this one. Classification of suspension system. There are 3 kinds of suspension system. One is a passive, number 2 is semi-active, and the third one is a full active. Right? Where passive suspension system, the damping characteristics are very constant. So we cannot adjust it. So that's a bigger problem in passive. If we go for a full active suspension system, everything can be adjusted, right? Using actuators. Hello, it's audible?
Your screen is in the first slide.
I don't know what I do. Stop sharing. I have done a stop sharing. See, share screen. Now it's okay. It's visible. Slide
Yes,
number
sir.
8.
Yes.
What.
Yes.
So for full active, we are having this actuator. So we are getting a good suspension ride and comfort as well as vehicle handling. But the penalty is we have to spend 10% of total output of engine. That's a bigger problem. That's the reason people are moving to semi-active suspension system, right? Where we are having some few car models. So just I'm not going to that one. Just I'm looking for this one semi-active only. I don't know. Slide is not moving, Francis. 1 minute. Okay, right. So I am just talking about the Magneto fluid, where rheology is a characteristic where external disturbances are as given to a system. What is external disturbances? It may be a stress, it may be a strain, it may be a temperature variation, or it may be a magnetic flux, or it may be a variation current, or it may be a variation voltage. So these all are disturbance on the system. When system is getting disturbed, its original characteristics is getting changed, right? So here, what we are looking for the changing of damping characteristics. That means it's in a Newtonian fluid. Normally, the MR fluids are called a non-Newtonian fluid. Initially, when current is not given, it acts as a normal fluid. When current supply is given, what happened? It became a non-Newtonian fluid. So, see this particular diagram where this black colored dots are ferric particles having a size of 8 microparticles, 8 microns, right? Average size is 8 microns, where the carrier is mineral oil. So initially what will happen, 30 by 70 by volume of ferric particles and mineral oils mixed together, right? This is suspending on the oil system, right? What happened when this system has been disturbed? How it can disturb? We are this slide is running, Francis. I am in 10th slide. Francis, slides are running. Hello, Francis, are you there?
Yes, sir. Yes, sir.
Yes. Okay. So now what happened? Here, this particular diagram number 10, direction of magnetic flux. I am giving a current input. What happened to these particles? These particles all become a chain. So that means, so it's not allowing fluid to flow very fast. It allows fluid flow in a normal condition or very lesser condition. So that's the reason people are looking for the MR fluid in automotive application. You know about there's something called damping characteristics where zeta value is very important. Damping ratio, zeta value is very important one. Zeta is equal to 1 means it is called critical damping, and zeta equal to more than 1 is called over damping, and zeta equal to less than 1 means it is under damping. Again, zeta is less than 1 means which kind of automotive application you can use. Again, there is trade-off. If like a commercial vehicles, they will go for 0.6 to 0.7 values. For formula vehicles, they will go for 0.9 to 0.15 because they want the damping characteristics very fast. Critical damping value, they have to get it. But the automotive cars, they are having values of 0.3 to 0.5. This is what they are using. So this is a weighted matrix. Why we are going for a semi-active suspension system? Go for the last column where ride and roll, comparing with the full active, it's getting some values. But go for the cost and energy consumption, it's very less. Even you can use a small battery of 12 volt battery. You can give a supply and the damper is getting actuated, right? So finally, performance weightage, I am getting number 10. So normally we are selecting this particular damper for automotive application, right? These are another some important characteristics. Ride comfort. We have to look this vertical vibration of 1 to 1.5 X and lateral vibrations 0.5 to 0.75 X. If these values are going more than 1.5 X, definitely it will affect the passengers or occupants inside the car. So always you have to keep less than these two values. One is vertical vibration value, another one is the lateral vibrations value, right? So the suspension system plays a very, very important role, right? So this particular slide is from ISO 2631. So if your values are 0.315, lesser than 0.315 meter per second square, you are in comfortable. But it ranges 0.315 to 0.63. It's a little uncomfortable. And when these values are increasing a little bit high, it is extremely uncomfortable. So we automotive people always look for I have to get the vibrating value less than 0.315 meter per second square. That's the reason people are looking for some good suspension system where there are two components are very important. One is called a vibration dose value, another one is called a motion sickness dose value. These are two individual components, but combining it give the input of the system where it will not affect the occupants inside sitting in the car, right? Okay, can go to slide. So how I am selecting a damper, that is very important one. So these are the few parameters I look for. One is what the load of that system should carry. That is one thing. I have to look for packages. That is very, very important in automotive suspension system. In lower volume, I have to keep the performance damper. That is very important one. And suitable damping value. That is why I told one is zeta value I'm thinking about. And the another value is damping coefficient value. That is two things I have to take care of. This is the third point. And how many number of cycles it's working. So normally people are looking for 20,000 cycles, 20 lakh cycles. So I have to ensure that 20 lakh cycle, my damper is not getting damaged, right? I have to give assurance to my end users, right? Next one is temperature gradient at which a proper function of the system is assured. So because the fluid inside is having a friction with the piston inside. So what happened? Continuously it is getting operated. There's too much temperature variation. If there's too much temperature variation, what will happen? Your damping value is in reverse. That means damping density is getting reduced. So viscosity is reduced. So it will affect performance characteristics, right? Right. We can go next slide. So this is a particular damper. Its damper is called long stroke damper. Right, when you see this damper, you're having these two wires here, where it's a positive and negative here, and this piston number 7 is there. C7, 7 is a piston. In piston, we are providing a copper coil inside, with thin wire copper coil. This copper coil will go through this piston rod area, and it will come out, and we are having two wires, right? Positive and negative wires. Right, where I am giving a current input to 2 wires. So I use a small ordinary battery. I can operate this damper into 0 amps to 2 amps condition. 0 amps means my damper works as a passive damper. So there is no influence on the electronic system or magnetic flux. But I am giving even 0.1 amps also, it acts as a semi-active suspension damper, right? So this particular damper, it was purchased from Lord Corporation from US, where I can operate this damper for 1 amps continuously. I can give a 1 amps current continuously. I can work it continuously. That's one thing. But I want to increase a little bit more. If I go for 2 amps current input, what I have to do? I have to use this damper into intermittent value only. I cannot use I cannot give a current input continuously, right? So I will show some graph taken from this. I use this one in a damper testing machine. The testing values are given here. See here, these are the condition I have fixed. My velocity of this crank arm of damper is 3.14 Hertz. That is I fixed it 100 RPM or 3.14 Hertz. That is I fixed. But I am looking for this industrial application. I tested this movement, linear movement of this damper into 0.05, 0.13, 0.26, 0.39 and 0.41 meter per second. That is talking about. Sorry, it is 100 RPM, 200 RPM. For 200 RPM, it's 3.33 Hertz. Sorry for that one. So I told about continuous current input is 1 amps. Intermittent current input is 2 amps, right? So I tested this damper from these various values. I tested in a 0 amps. 0 amps means it's a passive damper. If I'm increasing a 0.5, I am giving a current input of 0.5 and I'm giving a current input of 1 and giving a current input of 1.5 and I'm giving a current input of 2 amps maximum, right? So I have for doing this one, I am looking for these characteristics. One is the hysteresis, nil non-symmetrical hysteresis characteristics, pre-yield and post-yield region, role of effect. These are 4 things I'm looking for, right? So this is a 2 graph, is velocity versus force, right? So see this particular graph having black in color is visible. Francis, is visible, Francis? Hello?
Yes,
Hello?
sir, visible.
Yes, yes. So see this one, there is a, this arrow mark is moving. My arrow mark is moving. This also visible? Okay, no issues. See that.
Yes, sir, yes, sir.
Okay, I is idle condition. That means my current input is 0. It acts as a passive damper. So I am giving this linear velocity. What happened? This first quadrant is called rebound, and this is a bound character. Sorry, first quadrant is a bound, and this third quadrant is a rebound characteristics. Say I am giving a 0 amps. What will happen? My damper characteristics is coming like this. That means my damping value, my damping value, it goes up to 500 Newton meter per second. So 500 Newton. This is getting, this value is 500, and maximum this rebound damping, it coming around 750 this area, right? In damping coefficient, Newton second per meter. So it ranges from 500 to 700 Newton second per meter. But what happened? I want to increase my damping coefficient. So how I can increase? I'm giving a current input 0.2. Initially I tested with 0.2, but I'm looking for 0.5. I'm giving a 0.5. So that means what will happen? See, my damping coefficient value is increased from 500 to how much value? See here, it is nearly 1500 value. See, this maximum value is 1500 at a velocity of 0.4 velocity. But slowly when velocity is getting reduced, this is also getting reduced. But this industrial application, I'm looking for the high velocity. So it's a 0.4. 0.4 velocity, I am having a value of 1500 Newton second per meter. And the rebound value, it is a little bit more. It is coming around 1600 Newton second per meter. So I am giving a little more current input. So I'm leaving a 1.5. Just I'm talking about 2. So I'm giving 2 amps. So what will happen? Still, my damping coefficient value or my force value is getting increased a lot. So it is coming around 2000 Newton second per meter here. And here it is around 2550 Newton second per meter. So this damping, sir, initially it is only 500. Initially it is only 500, but I am slowly giving a current input. The damping value is getting increased, and it goes maybe 5 times, 500 times, 500% more than damping coefficient. So what happened? Why I am doing this one? Why this is doing this one? So my vehicle, my damper needs say 500 Newton second per meter damping coefficient value is going on a smooth road. So what happened when you're using passive suspension system? Even passive suspension system, even ordinary condition also, it will give 2500 Newton second per meter. For this particular case I'm talking about. So what happened? You always missing your right comforter. You always getting your right vehicle handling only. But if I am using this damper in a vehicle, my vehicle is running on the road, smooth road, where 500 Newton second per meter damping coefficient is enough for me. I can run that one. But when my vehicle is hitting on the bump, so, or my vehicle is in the pothole, right, where I have to give a current input, I can increase the damping coefficient, and my damping value is getting increased. So my ride comfort is enhanced. So I get a good ride comfort. Simultaneously, my vehicle also ensured my vehicle safety, or it is called vehicle handling, right? Next slide. So this is normally force versus torque curve. Force curve. This is this square curve. Normally we use. We will tell this square curve, and this is hysteresis curve. You already know aware of this hysteresis curve. When it is it's 0 amps. It is 0 amps. 0 amps. See, this curve is very small. 0 amps. This is in orange in color. It's very small. But I am increasing the amps value. This curve size is getting increased, right? I missed one thing here. I used say 1.5 2 amps. If the question may ask, if I increase more than 2 amps, what will happen? Right? This normally the question will raise. So what happens? This 2 amps will give saturation of the complete damping. Saturation of damping. So even though you give more than 2 amps current input, there will be no effect on the magnetic flux. So you will see here, even 1.5, see this particular graph here, 1.5 is giving a more damping value than 2 amps. That means in some area, 2 amps is giving good value, but maximum peak value 1.5 amps is giving. So that means at 2 amps, I am getting a magnetic flux completely saturated. After even I am giving 2 amps also, there will be no use, right? That is the meaning of this particular curve. And so this is what so normally my passive damper always having 2600 Newton second per meter, but I don't want that value. I only looking for the ride comforter. So during ride comforter, I have only 500 Newton second per meter. But my vehicle is in a bumpy condition, or it is a pothole, or it is a pothole, or it is a bumper. I am giving a current input of 2 amps. My damping value is getting increased. Right? You can go next slide. So while I am talking about this one, I have to give a current input only. I have to give current input only. So if I am giving current input, it will work. That is good. But I have to use some control strategy to change the density and other components of the current input. I cannot use an ordinary switch on-off condition. I can do it. I have to consider some factor, and I have to operate this damping at the precise time. Cutoff time is very important one, and the time of current input is another important one, right? So I have to go for some control strategy, right? So I am moving from material science to control strategy now, right? I am not going too much deeper, but I am giving glimpses of what's happening on the control system. If having any queries, so maybe you can mail it, or we will discuss during this session if time permits. So normally what happened, there is something called this particular strategy was invented by Carnot, K-R-N-O-P, by 1974, where they considering, this is my chassis. So I think you are all are mechanical people. The M2 is called as sprung mass. Sprung mass is nothing but a chassis, and M1 is called unsprung mass. Unsprung mass is below the chassis. So I can say the spring, axis, tires, everything called unsprung mass. So what happened? I put this is a spring and this is a damper. They consider I put a damper on this sprung mass and it is hanging on side. That is the meaning of this one. But it is not possible. I can hang a thing on the sky, right? So what happened? I consider my M2 sprung mass is my sky. So I put a C2, my damper here. So why this arrow mark is here? This means, this arrow mark here, this means this is called a continuous variable damper, right? You understand? CVD, sometimes called CVD or continuous variable damper. That means these damping characteristics are getting changed continuously. How it is working, how this particular is working? When there is a change in relation between Z0 is a road profile value. Z0 is a road profile value. When Z0 value is getting increased, what will happen? Z1 value also getting increased. There is a displacement. So Z2 value is increased. Z2 value also increased. So they put two sensors between Z2 and Z1. It is the infrared sensor. Normally they will put simple sensor they put. So when Z2 and Z21 are coming closer, Z2 and Z1 are coming closer, what happened? Nothing happened. The system, my spring is only getting compressed, but Z1 and Z2 is going away from each other. During the time, I have to give a current input to the system. My system is getting working. This is called a skyhook system, where if I'm using skyhook, the merit of the system is I get a good ride comfort. I'm not having a problem in a ride comfort, right? But what happened to ground hook? Now I put this one on the ground hook, where here if I'm using this one, my unsprung mass is very good. Vibration is very good, but my sprung mass vibration is very problem. So unsprung mass is very good means what will happen? My ride comfort is very good, but here my ride comfort is not support. So right, so these two strategies are having a demerits. The reason people are going, some other strategy is called a skyhook strategy, hybrid skyhook strategy, where here alpha makes a very important component. Alpha makes very important component, where sigma sky is a skyhook, sigma ground, this is G and D is a ground, right? So what happened? Alpha value is 1. Okay, so what happened? I put alpha value is 1 in this particular equation. What will happen? This 1 minus alpha and ground becomes 0. So this is 1 into alpha sigma sky. I get a damping coefficient of skyhook damping. In other case, I put alpha equal to 0 here. What will happen? Sorry, alpha equal to 0 here. What will happen? My sigma sky will diminish. My sigma ground will be good. So I get a good unsprung mass vibration. This is how it is working. But the problem with this particular hybrid skyhook suspension system, the switching is a bigger problem. So I am not getting a good ride comfort. Even though I put a lot of effort of getting this one, I am having problem in not getting right comfort. So people are not using this one. They will go some other system called skyhooks on-off strategy. So here what they will do, right here, very important thing of this skyhook on-off control strategy. The simplification is there is no any complicated controller components, right? I'm having only 2 sensors. That is enough for me, and I am having 2 level of damping. One is my I equal to 0. I equal to 0 means it is a passive suspension system. I equal to maximum means it's I equal to say 2 amps means I am getting a maximum damping. I cannot increase, again I'm reinstating, if I cannot increase I more than 2, right? Because I got already saturation, I cannot increase more. So I can put I equal to 2, So for the example, I'm telling I equal to 2. But some dampers maybe will give a current input a little bit more. I will tell you other classic example. You check in a Google Scholar or somewhere else. We are having some bigger size of dampers having a 500 tons dampers also available. 500 to 600 tons dampers available. These dampers are used multi-story building. So these keep this damper on the ground floor, right? They keep one eye point on the ground, one eye point on the building. What happened? Why we are using this kind of damper? When you are getting small kind of earthquake and all the things, this damper absorbs shocks from the earth. Normally it will absorb shock from the earth and it reduces transfer of the shock from earth to the building. So check it. Many high-story buildings are using this kind of MR dampers are used in high-story buildings, right? So here I am having two things. My Z2 and Z1 comes closer, not having any problem. My spring is getting compressed. I allow spring to compress because it is my M2 is coming to M1, right? But my Z2 is going apart from my M1. What I have to give my current input, right? So after my Z2 and Z1 is in constant position, or my vehicle is going on a smooth road, I'm not having any problem. So at the time I will stop my current input. So if it is having a bump, until go to bump, it is getting compressed. After it is coming from the bump, so my Z2 and Z1 value is going apart from each other. I have to give a current input. When reaches in normal condition, so I am not giving any current input. So my system will get a good my system acts as a passive, right? When it is having a bump, until bump, it is my passive suspension is a passive, but it's a bump, and hitting a bump from coming downside, my system is getting activated. So where this particular damper used a lot of support on getting a ride comfort as well as a vehicle handling. So I am looking for the two things I told you: C high state or C max, damping coefficient maximum value, C minimum or C low state. These two things I am working on it. I am getting it, but still I have some problem in precision controlling of the switches and all the things, right? All the things. So people are using a fuzzy logic things. So I will show one controller system. So this particular this one off-car model is called a roll model. This kind of model is called roll model. What happened? The other model is called, we are having a few models. I will tell you, one is a quarter car model. You take one portion of the car. So that is called the quarter car model, where you only get a vertical vibration only. The another model is called a bicycle model. So what we are using, it is a two-axle model. Sometimes we call it as a two-axle model or bicycle model. You cut your car on sideways, right? So you look like this is sometimes called a pitch model. But this particular model, this you cut the car from the front end. So you are having a front tire here, front left and front right. So it is running on the roller. So I put a few conditions to control system. I use this fuzzy logic control. I am having bumper, and I am having control to MRD, where I have to give current input. So I consider serial number 1 is a left. You see, there's a bump is given. This is a 3 centimeter bump is given here. So consider first condition. I am having a 0. I am not having a bump on left, and I am not having bump on the right. That is, I am considering that the reason I put 0, 0. Right. So both the sides are 0 means. So that means you see, I kept a damper here. MR damper is here. See here, my damper is here. So that means I don't want disturb my damper. I work this damper as a passive system. So I'm not giving any current input to the system. So it is a 0, 0. Right. Next, I am having a bump on the left. Right. So I've given this is also some assumption value. Right. It's a fuzzy logic. Yes or no. Right. That's the reason I put 0 and 1. This on right sides 1 is I am giving 2 amps current. Okay, please remember This one is a yes or no. Right side, its current input is 2 amps, but for our understanding, I put 0, 1. So here, I am having a bump on a left side. So I put a 1 here. So that means I have to give a current input on the left damper only. Right damper, I don't want to put a current. So that means a right damper works as a passive damper always. But a left damper, I have to give a current input of 1, current input of 2. So when it crosses from the bump, my sky hook on off suspension system, control system gives a current input. If I go to the third option, is 0 to 1. That means it's in the right side. I am having a bump. So I have to give a current on the right side only. Right. And fourth condition, this condition, I am having bump on the both the sides. That means when the tire crosses this bump, I have to give a current input to the both the MR damper, right? Manual damper. This is a fuzzy logic. I have to put this logic and I get some values of that one. Right. This is the other one. Maybe I discuss this slide. It will take some 10-20 minutes. So I'll go next slide. So this, I think you have studied the fuzzy logic function. I keep 3 values. At the time, any one value only having a maximum value of 1. See here, say this is a front and this is a rear, and there's no current input. So left means it's having current input. Here it is 0. See, all other 2 values are 0. The another one is neutral function. So this is my 1. Other 2 values are 0 here. If MF3, this is 1 value. The other 2 values are 0 here. Right? Okay. This is one particular this work has been tested. This is a vehicle, and this is a preview control system. So I give a current input here. I just current input here my sensors. So what happened? It gives a current input to my rear damper. So my rear damper has started to working. Right? This is where few things are very important. My time delay respected to vehicle preview distance. So I have to calculate what is the wheelbase from center to center. That is one thing I have to calculate. What the speed of my vehicle is going. 2 things I have to calculate, right? And preview distance. This is a failure model because sometimes even water or even sandy will not give a hot surface. If you're not giving hot surface, but your preview sensor will give a wrong information to my control system. So my control system will give a wrong direct instruction to my MR damper. So my current input is wrongly given. So even though the road is not smooth, the MR damper started to working. So I don't want to take a risk. So I have do something impulse system. I give a bad bump here. So I get a bump here. Yes, immediately IR sensors here. I'm getting current input. So it's work. But the problem is, I told you, I think I missed it. One thing is, this reaction time is 15 milliseconds, 10 to 15 milliseconds. It's the reaction time. But my bump, my tire crosses even 5 milliseconds. For example, it crosses 5 milliseconds. So what happened? There's a 10 milliseconds time delay is there. 10 milliseconds time delay is there. Because of the time delay, again, my damper will not work properly or work after my tire crosses the bump, right? So this is not this is also not suitable for this one. So that's the reason we keep this input based control where a few sensors are used. This particular thing you are using IR sensors here, and there will be proximity sensor used in a steering system also. So if I told you, when it is coming closer and it is going apart from each other, immediately it calculates and giving a current input to my controller system. So this is controller system and control algorithm and my MR damper will work, right? So for this one only, I have given this table, this bigger table. See this particular table. I will take this one. I will talk about this one. Go to fifth one. Not fifth one. I will go some other point. 1 minute. Yes, I will go 9th one. I am having a bump on left side and right side. Right. So that means I have to give a current input to left damper and right damper fixed on the rear wheel. But I kept the other condition here. Before I shown this table for a half car model, but this is for a full car model. I have to consider my steering rotation. So my steering rotation is minus theta in the right. That means I am turning my steering wheel on right. That means right. I have to give a current input on the left side only. Right. I am taking an inner turn for your understanding. I can say I can take an inner turn. What will happen? Inner tire will go up from the tire and the outer side tire is getting compressed. So what happened? There may be a chance of a roll of the vehicle. So what I'm doing, my inner tire is going up. I'm taking inner left turning. My inner tire is going up. So I don't want to allow my vehicle to roll. So what I'm doing, I am giving a current input to the damper fixed on the right side. What happened? My damping coefficient value is increased. That means, say my vehicle is rolling on 10 degree. Because of this damping, increase in damping coefficient, instead of 10 degree, it will not go 10 degree, it will go maybe 4 degree or 5 degree. That means my roll of my vehicle has been reduced a lot. So I use this one. So what happened when my steering rotation is being considered, I have to operate based on steering condition only. During the time, I don't want to worry about my bumping position because ride comfort is not important during this crucial time. Vehicle handling is very, very important. My vehicle will not go for the topple down during taking a turn on the any turn, or during high speed cornering. I have to give a damping coefficient on the outer wheel, not inner wheel. It will reduce the rotation of the tire. Rotation of the roll angle, right? Reduce the roll angle, right? Got it. Right. So I am talking about this extended controller, and we are having some other controller, but this specific forum is not focusing on this particular thing. But just I am throwing some information. If there is a fluid called MR fluid, this MR fluid at the current date they used in various applications. One majorly they are using in the automotive application, especially on suspension system they are using. In automotive application, there are other two applications. There are few modes are there. One is the skews mode is there, slide mode is there, the torque mode is there. For other mode, they are using a clutch, inside clutch they are using. Second, third one is a brake rotor they are using. So in automotive application, they are using in three major areas. If going for a building, they are using this to reduce the building shake. This second application. Third application, in the prosthetic legs, people are making prosthetic legs. While you are walking, your original leg will give small amount of cushioning effect. If you keep a artificial leg, this artificial leg will not give that cushioning effect. That's the reason it has been fixed with a small kind of MR damper. So you feel that means you are walking with your original limb, not using an artificial limb, right? So these are some strategies. Please note it down. If you're having queries, maybe we'll discuss afterwards. HNF2 is one kind of controller people are using. The very important thing is because I'm giving a continuous current input on off. What will happen? There will be, I'm lost the stability of the MR damper. So I want my system has to get a good stabilization. I have to use this kind of damper, H infinitive. Next one is linear LQR damper, where I am having three things. I am having a linear quadratic regulator. I use this one to enable a closed loop. Normally, this all control system is not used in an open loop. These all are closed loop. I have to give an input. I have to measure output. If I am having problem in output, or I am having problem in a targeted output, because we fix a targeted output. I am having problem targeted output. Closed loop thing will give my controller. There is a problem happening in the outside. You change it. So accordingly, I will change the current input or any parameter what I am fixing, I can do it. But here, especially MR damper I'm using, I am using only a current input. I can change the current input and I will get the final output. This is a LQR regulator, linear quadratic regulator. This second one. And third one is the PID controller. You know this one, proportional gain, integral, and another one is the derivative. So I am having three components here. So this is a suspension system model. This is suspension system model. I am looking for the 4 component. Why I am using a suspension system? To reduce the vibration, but where I am measuring 4 components. What are the 4 components I am measuring? I am measuring a car body displacement. This is nothing but a sprung mass displacement. That is X value. Next one is the car body acceleration. That means I am looking for the sprung mass acceleration, X double dot. Third one is the suspension travel. This is nothing but x1 minus x2. Normally, automotive people, we tell this is called a rattle space displacement. Rattle space displacement. Next one is the what is the amount of wheel is traveled. So this all I tune these 2 values. I think I have another graph here. So I am having a KP, KI, and KD. See this particular one. I keep KP1, KP11, KP21. I keep this controller and I run in a simulation. I do continuously doing normally error and trial basis only, because of people still get a knowledge what the value I have to get it. So I'm doing error and trial method. I do all the things. Then finally I get the final output. So if I'm using this kind of controller, I do tuning on like IC engine we are tuning, injection timing, crank angle and spark timing we are doing like this. We are tuning these 3 components, proportional component, gain component, integral time constant, and derivative time constant. You are doing fine tuning and we are getting the final output and the estimated output we are looking for. And this one is people who belongs almost or expertise in material science. These are various models we are using. One is a model, some description and examples. One is called a quasi-static model, where this model is based on a bin gum plastic model. This is the first model invented, bin gum plastic model. And slowly what happened, this model has been kept in deeper research, and every time this model has been modified, and we have a lot of models. One is a modified bin gum model is there, and a biviscous model is there, viscoelastic plastic model, stiffness velocity, viscosity elastoslide model. So like this is Boak-Wen model. This model is extensively used, Boak-Wen model, and sometimes we are using a hyperbolic tangent model. Equivalent models also we are using. What happened, while we are doing a simulation, we use these various models and we can finalize. There is always a trade-off between one model and another model. Always one system and another system. But our objective is we have to get a optimum performance of the system. So which optimum, which one looking for, right? We know about the spider diagram, where I put a cost, ride, roll and vehicle handling. I put all the components where which one giving an optimum performance in all the aspects. I will write this model, and a lot of research work is, especially people know about CFD and people know about material science. And yes, the two expertise can use this particular. This is simple title I have given. You can use this one for your research work, or maybe for your ME thesis or some other work. There is some model like a black box model and the things, a neural network model. Nowadays we are using a ANN. Yeah, ANN and physiological also they are ANN model, and they do a lot of research work on this particular models, right? So if again if I use this model, this all models are used in a MATLAB. MATLAB, I put this equation and I get the final output, right? And this is a physical full car model. I have explained previously. This is after model testing. This is some values I got from that particular thing, right? With this, I can stop. If you having any query, let us discuss. With this, I can stop it, right? Thank you. Dr. Francis.
Yeah, thank you, sir.
There are few questions asked
Yeah.
by people. Maybe one question is new messages is from somebody else. Is Shashikant Koilkar. Is the damper temperature rise is also major issue? Yes, every damper, right? They put Department of Transportation US brake fluid they're using for Formula racing. They're using a .5 fluid because every time you are pressing a brake, it's getting 500 degree to 600 degree temperature. This damper is normally a fluid. If temperature is getting increased, there is something called viscosity index. We have already studied. When rises temperature, reduce in density. If reduce in density, what will happen? You will get a spongy effect. If having spongy effect means your damper act as a soft suspension system. That means you will get only ride comfort. You will not get a vehicle handling. But while you are taking a turn, right, or something called DLC and SLC. SLC is called single lane change. DLC is called double lane change. Especially simple thing, you are overtaking one vehicle and you are overtaking two vehicles simultaneously. During the time, what happens if your fluid become very soft? That means it will not support to vehicle handling. So temperature variation is very, very important one. People who are in this group, people in this group who are interested doing CFD analysis, think about fluid flow analysis in the damper in variation temperature, right? So you can use a COMSOL software. COMSOL is one of the finest software. You can use, you can get output, right? Okay, yes, normally above 80 degree. Yes, Shashi, it is normally above 80 degree, right? Right. Any questions?
Yes, dear participants, you can unmute yourself and you can raise your queries.
Sir, sir, I'm Srinivasan.
Yes, Srini, please tell me, ma.
Sir, you are using either you are going to switch off or you are going to switch on with the 2 amperes with your damper. Why don't you use this middle values? Because as you said, actually, more damping means more power loss. So why don't we use this middle values?
No, I'll tell you.
Between this 0 and 2.
Good. Thing is, I think I shown this diagram. I use this one for one. Okay, slides are not moving. Okay, no issues, sir. My damping, I use this particular vehicle of 300 kg for example, where 300 example, I do analytical calculation and numerical investigation, and I found damping value is 2600 Newton second per meter. Right? For understanding, I'm telling you, right? This is a maximum damping value. But if I'm going in a smooth road, I don't want a 2600 Newton second per meter. I only need a 500 Newton second per meter. Okay, where especially I selected this particular vehicle, this required, say, I can say in case, in other way I can say I need a 0.6 damping coefficient value. 0.6 means I calculated, I get the value of 2600. So I keep the 2600 value for my particular vehicle, where if I keep 2600 value, then only I will get a good ride comfort. Then only I will get a good vehicle handling. Otherwise, I will not get it. If I reduce the 2000, I will not get that value. So the reason I fix that value. I think I answered your question.
So, but whether this value is always the case, because if this is a smooth road or there will be a very small bump, there may be a large bump. So if you are taking,
yes. I will tell you.
What
yes.
difference we are?
This question, I will tell you. Especially, still research, a lot of research work to be done on this dampers, right? Where I can change these values from minimum to maximum only. If I do not know what the size of bump and what the size of potholes and what speed my vehicle is going. Right? I'm having a little bit confusion. So the what you are talking about is the other PhD work. I do all the values, maybe 1,000 values I can put here. If my bump is 1 centimeter, my vehicle is going on a 20 kilometer per hour, I give a 0.5 amps. For example, my bump is 5 centimeter, my vehicle is going at 50 kilometer per hour, I have to give 1 ampere current input. So like this, I put all a fuzzy table and I can incorporate it. I can do a programming. Then I can make a controller where this adaptive controller, like adaptive QC control, this adaptive controller will understand what the speed of my vehicle is going, what the bump is hitting. Accordingly, I can give a 0.5 current input or 0.2 current input or 1 ampere current input. Any current input I can give. But at present, with the existing technology, I can use a minimum maximum only. I cannot incorporate in other things. I think
adaptive fuzzy controllers are available, isn't it not?
Adaptive fuzzy control available, but again, a few values. I can put 5 values.
Okay.
Only 5. But my vehicle is moving on the road. It's various speeds going, various bumps, various potholes goes. But especially controlling the damper, adaptive controller is still not existing. It's working on 2 conditions, maximum and minimum condition only it will work, or maybe 3 conditions, 4 conditions only it will work. It will not work in this huge range.
Okay.
I think I answered the question, right?
Yes, sir. It needs a lot of diagnosis, so it is not possible.
Yes, ma. Lot of maybe this may be another research work.
Okay, sir. Thank you, sir. Thank you very much.
Ma, anything else, ma? I hope, dear participants, you understand because the 40 minutes, 45 minutes, I cannot explain this one. Even I'll tell you, LQR controller itself 45 hours course, HNF controller itself a 45-hour course. Right, and M and damper only fluid analysis, again it is one PhD work. So just I'm giving a thoughts, what are the things are available, what kind of research work you can carry out. Right, that the idea I have given this presentation. Anything else, any questions, sir?
So if no questions, thank you, sir.
Thank you.
We will share your mail ID. Thank you, sir. We will share your mail so that if any queries, they will contact you through your mail.
Definitely.
So, thank you so much, sir. And I would like to express my heartfelt appreciation for your remarkable presentation of this FDP. Your insights on this today's topic on control strategies on Magneto Rheological damper for automotive applications were enlightening and interesting as well as meaningful. So on behalf of Department of Mechanical Engineering, Swarnandhra College of Engineering Technology, West Godaveri, Andhra Pradesh, and thank you, sir, for taking the time with us as a guest resource speaker for today's session. Also for accepting our invitation in a short notice. Thank you so much, sir.
Thank you, Francis. Thanks for inviting. Thanks for the management and the HOD for providing opportunity. And thanks for patiently listening participant. Even there are 75 participants are there. Still cricket is going on. 26 for 6, if I'm right. Okay. So I think I disturbed your this.
Thank you for your update. Thank you, sir.
Thank you, ma. Take care. And
thank you.
Somebody is asking a question. Sasikanth, maybe we'll discuss afterwards. Sashi, we'll discuss afterwards.
Yes. Thank you.
Okay. Thank you.
So, yeah, dear participants, the attendance and feedback form has been posted in the chat box, Zoom chat box, as well as in the YouTube live chat box. So it will be active for the next 15 minutes. And I would like to express our appreciation to all the registered participants for actively engaging yourself in this knowledge sharing faculty development program. And we are very much thankful for your interest showing towards this knowledge learning. And tomorrow we have two sessions. And session one by Professor Dr. V. Manivanan under the topic Additive Manufacturing in Production and Innovation of Making Materials from Sri Sai Engineering College, Chennai. And the second session is by Dr. K. Karthik, Assistant Manager, Ola Electric Technologies, Bangalore. He is going to present the topic on future of electric vehicles. Dear participants, the link will be active for another 5 minutes. And thank you for your active participation. Those who submit your feedback, you can log out. The link will be active for another 5 minutes. Thank you. We'll see you tomorrow.